Just for some background, I've been in the business of doing computer simulations of the operation and planning of electricity supply systems, large-scale systems, for over 35 years now. Gosh, it's scary. And although that's not the only thing I do. So what I propose to do in today is, now where do I point this thing? There? No? Here? Here, okay. Okay, so what I'll do briefly is discuss the context, perhaps build a bit on Gavin Mudd's introduction, and then focus on two areas where those who are very enthusiastic about nuclear energy like to try to criticise renewable energy, and that is the reliability and the economics. And I'm going to argue that we can provide 100% renewable electricity systems which are just as reliable as conventional polluting systems, and they are now becoming cheaper than any kind of system that is commercially available that would have a large input from nuclear energy. But for background, well, Gavin Mudd has already shown this slide, so just to remind you, the bars show the annual energy generation, and you can see it from nuclear energy. It peaked in 2006, and since then it has been declining slowly, and the percentage has declined from about 17.5% in the mid-1990s, well, actually today to just over 10% of electricity. If you look at the reactor startups, which are in green, and shutdowns in brown, you can see that after about 2010, we reached a stage where there is almost balance between startups and shutdowns. And if we look forward, we've got a lot of old nuclear reactors. France is shrinking. It's not going to rebuild a lot of its present old nuclear reactors. So it's quite likely that shutdowns will exceed startups. If we look at global investments in renewables versus nuclear, nuclear is the red line, and because we can't identify when a project starts each year of the nuclear investment, this graph from the World Nuclear Status Report puts the total nuclear investment costs into the year in which construction started. So the red line is nuclear, and the bars are renewables. Solar is in the green, wind in the blue, and other renewables in the paler colour on top. And by the way, the decline in solar in the last 3 years on that graph is not due to less solar being put in, or very slightly. It's due to the fact that solar is getting cheaper and cheaper, and so the investment costs per megawatt or gigawatt or whatever of solar are declining. The writing is on the wall. Now, clearly on a global scale there is no renaissance in nuclear energy, but there are a few countries which are building nuclear fairly rapidly, and the main one is China, and then there's to some extent Russia, South Korea and India. Well, let's look. This shows the installed generating capacity of nuclear in the red, wind in the blue and solar in the green. And you can see what's happening. This is in China. Now, okay, of course, someone will say, well, yes, but they have different capacity factors, and that's certainly true. But even if you allow for the difference in capacity factors, you can see that wind has overtaken nuclear in China, and solar, well, it's got some way to go in that regard, but the trend is fairly clear. So the background suggests that we're not dealing with a thriving industry, and even in China, which is investing in everything, in big fossil fuel generators, while it's closing down some of the older and less efficient ones in nuclear and renewables, even in China, you can see that renewables looks like it's going to take over. And by the way, nuclear in China currently contributes about 2.5% of Chinese electricity. So it's not a major source. Okay, so now I'll try to talk about reliability and then economics. And the first thing to say is that those who are enthusiastic about nuclear and hostile to renewable energy usually misrepresent the whole reliability issue, because the reliability of a generating system is measured by the reliability of the whole system, not by picking out a solar PV or wind and saying, oh yes, it's less reliable than nuclear. It's the reliability of the whole generating system. And this can be measured, is measured in different ways by electric power engineers, and it's quite obvious when you sort of see the anti-renewable energy literature that it is not written by power engineers. It's written by biologists and occupational therapists and people like that. So the three main measures of reliability of a generating system are the loss of load probability, more precisely the expectation value of the probability that supply fails to meet demand, and that's used in many electricity grids. The frequency and duration of system forced outages. So forced outage is when supply fails to meet demand. And in the Australian national electricity market, the shortfall in energy, which for the NEM has to be less than 0.002% of annual electricity demand. So they are the standard measures, and there are a few others too, but they are whole system measures. The wrong way to try and measure the reliability of a system is to look at the capacity factor of individual power stations, which is a very poor measure of reliability even of individual stations, less so for large baseload stations like coal and nuclear, but for any other station, the capacity factor depends on the operating strategy, which in turn depends on the nature of the electricity market and so on. So, for example, you wouldn't say that a gas turbine, which is a peaking plant and might have a capacity factor of 5%, is unreliable. But many of the critics of renewable energy would try to do that to renewables by saying that wind in South Australia, where some wind farms have a capacity factor of 41%, well, they say wind is unreliable because some nuclear power stations, after many years of operation in which they performed very poorly, have now reached 90%. So capacity factor of individual power stations is not a measure of reliability of the system. Neither is a quantity called dispatchability. And dispatchability is the ability of a power station to supply power on demand. And as you'll see, it is quite unnecessary to assume that every power station in a supply system is dispatchable. Even if we look at individual power stations, sure, nuclear is usually dispatchable, but if it has a breakdown, if it has a forced outage, it is usually down for weeks or months, or in some cases for years. Now, this doesn't happen for variable renewable sources like wind and solar PV. They tend to fluctuate on a timescale of hours or days. And we're currently doing an analysis of 30 years of weather data in Australia on wind and solar, and we'll be reporting those results soon. They're very interesting. So you could argue that nuclear is unreliable, but has a different statistical unreliability than wind or solar PV. Okay, so, well, before I actually get onto the computer simulations, I want to sort of point out that not many years ago, I remember when I was doing research on wind power, those who thought they knew better were saying, well, the most wind power you could have in a grid would be about 5% of annual energy. Beyond then, the fluctuations in wind would make the stability of the system impossible to operate. Well, 5% was passed in several parts of the world. Then they said it was 20%. Now they're saying, what are they saying? 30%, 40%. But the reality is that Denmark is generating now 39% of its electricity from the wind, plus nearly 10% from agricultural residues, from bioenergy. It's a flat country, so it doesn't have any hydro, a bit like South Australia for different reasons. And then if we look at states, if we're interested in South Australia, maybe we should compare with states. Two North German states, Schleswig-Holstein and Mecklenburg-Vorpommern, again, Mecklenburg-Vorpommern, try and get the pronunciation right, are now running at 100% renewable electricity net. Now, the net means that they trade with their neighbours. Of course, they trade by transmission line. But they are running at 100%, and in one of those states, over 100% net renewable electricity. Now, the critics will say, oh, you can't run a system like that. It will be unstable. Well, they're doing very nicely, thank you, in those North German states. I have searched the literature. I read a little German. I have tried to find major problems in operating in the stability of these systems. They're not there. And the interesting thing is that those two North German states are mostly generating from wind. Now, I wouldn't recommend 100% from wind. And certainly South Australia has fantastic solar potential as well as wind. And so we are looking not at comparing with wind alone, or as one recent article tried to compare nuclear with wind alone or nuclear with concentrated solar thermal alone, but we're looking at comparing with a whole mix of renewable energy sources. Now, in the computer simulations that others and we have done at the UNSW, we are running the national electricity market on a model with a mix of renewable energy sources. We don't claim to be the first to do this. These are some of the latest studies, and the references in a report I've written for the Conservation Council of South Australia, which will be released tonight. So, and these studies are mostly simulations, hour by hour, balancing real weather data on renewable energy supply against real demand data. Most of these studies now run for 8 years, and although our published studies in 2012, 2013 and 2014 were only run on 2010, the new studies that we'll be publishing soon run on 8 years. And I can tell you it doesn't really make significant difference to our results, going from 1 year to 8 years. We also, as I said, have a 30-year data set, and we are analysing that. So we are modelling the yellow region, the so-called, grandiosely called national electricity market. And so all those states are joined together by transmission lines, but the links, some of the links are not very strong. The link between South Australia is only joined directly to Victoria by 2 lines. They don't have high capacity, and although there is a small, an increase going on, we would recommend something more substantial. Tasmania has a modest link, and the link between New South Wales is modest. So the only really strong link is between New South Wales and Victoria. So what we've been doing, and this is the work of a former PhD student, Ben Elliston, who designed our computer program, assisted and supervised by Ian McGill and myself. And so we are balancing supply and demand every year, hourly, for 8 years. And we find that we can produce a system that is just as reliable, that meets the reliability criteria using real data. We're also doing the economics. So we've used the cost projections by the Bureau of Resources and Energy Economics, BRE, and their 2012 projections were very conservative for renewable energy. And I can say this because their projections to 2030 for example, the economics, the cost of solar PV, were surpassed last year already. And they've also made some rather heroic assumptions about the future price of fossil fuels. So they assume that gas in 2030 will have the same price as it did in 2012, which may be, but rather unlikely. We do have a simplified transmission model but we've done a very detailed sensitivity analysis. And although we think that if we put in more transmission links, there will be some increases in costs, the results aren't really sensitive. So anyway, so in the papers that we've published so far, which our critics don't cite, they only cite the 2012 paper. So this is the 2013 paper. Putting in the BRE costs, what we can do, because the computer program runs in about half a second for a whole year, and it's by the way available now. It's called Nemo. You can actually download it and use it. It's a public thing, open access. This is the optimal mix. If we do several hundred or several thousand simulations, we can vary the mix of renewable energy. We can vary the operating strategies for storage in the system and for the whole system. And so, for example, we find that the optimal behaviour of concentrated solar thermal is not as baseload as some of its enthusiasts say. We'll come to that. But what you can see here is that wind is nearly 50%. All these simulations are constrained. They have to meet the NEM reliability criterion. They are reliable. PV is 20%. So 2/3 of annual electricity generation are coming from variable renewable energy sources. How is this possible? Because the variable sources are balanced by flexible, dispatchable sources. Gas turbines, and they can burn renewable gases and liquids, or they can burn natural gas and other fossil fuels. Hydro, existing hydro, which you don't yet have in South Australia, but you could perhaps have, and we'll come to that, and concentrated solar thermal with thermal storage. Wind is such a large proportion because it's the cheapest of the new renewable energy sources, and PV is the second cheapest. So CST is the most expensive, there's no doubt about that, but its price will be halved within 10 years, the way as the market grows. Just like what happened with solar PV, except not as fast. So this reliability occurs because there is this balance between the variable renewables and the flexible dispatchable renewables. So basically, we've busted the traditional myth, 5 minutes, which claims, which is in the top graph, showing a day's demand in summer, and the traditional view is that the baseload, which is the blue at the bottom, the baseload demand has to be supplied with a baseload power station, but baseload power stations are very inflexible in operation, so you have different power stations sitting on top meeting the peaks, which are more flexible, like gas turbines and hydro with dams, and the assumption is that you've got to have baseload power stations supplying baseload demand, and that all power stations must be dispatchable. The new model, and it's not just ours, it's the study, the huge study done by 100 engineers and scientists for the National Renewable Energy Lab in the US. It's the studies done by Heidi and Greiner and Rasmussen and others in Europe. We all come to the same conclusions. The new concept is that you have the variable ones, as Vince Duffy said at the beginning, substituting for baseload energy, and the zigzag is filled in by flexible dispatchable sources, which are traditional peak load plants plus concentrated solar thermal with thermal storage. Okay, I'm going to talk about economics. I'm going to have to hurry. So economics depends, as you can see, on 4 variables: the cost of construction, or the capital cost, the capacity factor, the cost of finance, which is very important for nuclear and for renewables, and the magnitude of the subsidies. And with nuclear, the problem is that the cost data are less available than they are now for renewable energy. Credible cost data comes mainly from Western European and US power stations under construction. That's the current generation, called Generation 3, or grandiosely some of them called Generation 3 Plus. And we really have very limited operating experience with this current generation that's supposed to be a little bit safer than the Generation 2 reactors. There are really 2 main ones under construction, the AP1000 in the US and the European pressurised water reactor, the EPR. But really, none of these is actually operating. There's some under construction in China too, of both types, it's hard to get data. Now, the nuclear enthusiasts are saying, oh, well, we go to generation 4. Fast breeder reactors, integral fast reactors, they're unlikely to be commercially available for decades. I mean, that's the reality. Okay, so let's look. So there's a wide variety of cost estimates. The best one that's used, the one to promote nuclear, is the US EIA estimates. And these are averages for the US in dollars per megawatt hour. So nuclear, 96.1, onshore wind, 80, and utility scale PV, 130. But the second one comes from Lazard. And Lazard, as you probably know, is one of the biggest multinational financial services corporation in the world. They finance energy systems. They don't care whether they're nuclear or fossil or renewables. And their estimates are nuclear, 124 to 132. And they've tried to remove the subsidies, but with nuclear, the only obvious subsidies you can remove are the direct federal government ones, and all the others, which I'll mention, very hard to do. Wind, onshore, 37 to 81, and that's after removing the subsidies, which is 23 cents a kilowatt hour US for the PTC in the US. And utility scale PV is now, the new ones are now less than the nuclear estimate, according to Lazard. But what about practical experience with construction? Now, in the US, there's AP1000 reactors under construction, the Vogtle reactors. Now, different literature says different numbers of years behind schedule, so it goes from about 1.5 years to 3 years, and the budget goes from about 700 million to 1.4 billion over budget. These are all being built with huge loan guarantees. What about the UK experience, or the European experience? In Finland, with the EPR, Olkiluoto 3 is a decade behind schedule and is 2.7 times the original budgeted price. In France, Flamanville 3 is 5 years behind schedule and 2.7 times the budgeted price. In the UK, the proposed Hinkley C has been offered the builders of this power station, if they ever build it, a guaranteed price of £92.5 per megawatt hour, about $140 per megawatt hour, double the wholesale price of electricity in the UK, increasing with inflation for 35 years. So that's higher than the highest Lazard estimate. It also will receive a loan guarantee of about $10 billion. Okay, I've got to wrap up. So subsidies, there's a huge range of subsidies. I can't go through them now. Can nuclear and renewable energy be partners in low carbon electricity systems? Well, in brief, nuclear power stations lack sufficient flexibility in operation to handle the fluctuations in variable renewable energy. They are a very poor partner. The best partners are peaking stations, which are highly flexible, and concentrated solar thermal. Also, nuclear is going to have a problem if anyone ever seriously tries to introduce it into the national electricity market, that its operating costs are higher than those of wind or solar farms, and so it'll be displaced in operation, so it won't be able to operate as baseload. It'll be displaced by wind and solar, unless they change the rules for doing that. So finally, well, first, renewable energy. We could run the whole national electricity market on renewable energy if we have the political will, using commercially available technologies. Equally reliable. Nuclear appears to be roughly twice as costly as onshore wind and will soon be overtaken, and it is being overtaken, by large-scale solar PV. Nuclear is too inflexible in operation. And you could add to that the concerns it is increasing the risk of nuclear war by making it easier to proliferate undercover. It's a very slow technology to build, and the question of life cycle CO2 emissions means that it is higher in emissions as you go to low-grade uranium ore than a renewable energy mix. Thanks very much.